Swayam Prabha. Digital India. Educated India.
Welcome back. Today we are covering the design for wind and seismic effects. It's a broad topic trying to cover in 1 hour lecture. It's just the essence, okay, so that you can correlate with whatever will be covered by Professor Liberato subsequently. Now, why it is effects? See, these are not just force-based design. Today he mentioned something called control of deflection. Now, we are not talking of any of this. Okay, this is a pretty high end. What we are going to cover is first analysis for wind forces. Now, this analysis means how do I compute that what are the forces a building should be analyzed to consider the wind effects. Next, very briefly, the design. Okay, only the essence. Next, similarly, analysis for earthquake forces. How do I compute the forces which will be applied on the building to know what are the internal forces? Brief design for earthquake forces, and then I'll be touching upon computer aided analysis for gravity loads and lateral loads. Now, a good reference for this particular course is the book on reinforced concrete design by Professor Pillai and Professor Menon. The 4th edition, chapter 19, covers this analysis of the forces for wind and earthquake effects. Now, what are the relevant codes? 875 part 3 is related with the wind loads. 1893 part 1 is related with the earthquake loads, specifically for the buildings. IS 4326 is related with earthquake resistant design for low-rise buildings. 13920 is for the detailing, which I'm not going to touch today. 15498 is a special purpose code for improving the cyclonic resistance. We do have some detailing requirements as per SP34, but please note SP34, the earthquake detailing are very minimal. Analysis for wind forces. Now, why does we analyze for wind, or it is called wind load? Because it generates because of the obstruction to wind flow. It's a physical force which arises due to the pressure that is generated during this obstruction. Now, it is different from dead load, live load, the gravity loads. See, the gravity loads are there every second, at least the self weight, the superimposed dead load. Wind and earthquake, these are transient effects. It just comes once in a while. But then for wind, if I'm talking of precast buildings, the damage can be quite high. Okay, wind acts primarily in the horizontal directions. Why I'm saying primarily? Because if I'm talking of inclined roofs, we have already seen in industrial structures, they go for inclined roofs, then the loads are perpendicular, considered to be perpendicular to the plane of the roof. It is dynamic in nature, unlike gravity. Gravity is considered to be a static load, whereas wind load is dynamic. I will not go through all the lines. Please read it. What I would strongly suggest that read this material right here itself. Once you go back to your parents' institution, you will not get the time, and this will be just shelved. That's why please read whatever the handouts have been given. It is reversible in nature, unlike gravity. It depends on the location in the earth. Whatever we design for the east coast region of the country, We don't have to do that for the rain shadow area of Karnataka. The wind load depends on the height from the ground, the terrain, whether it is a hilly terrain, whether it's a valley, and it is uncertain in nature. The last one is the most challenging feature of both wind as well as earthquake. And hence the high-end wind analysis is a probabilistic approach. Now, what we are going to study today is a deterministic approach, okay, where we are looking into only the horizontal forces on the building as a whole. Build analysis is done in two steps. First, the building as a whole, and then component level. The component level gets important for precast members, more so if you have facade elements. Okay. That's what it says, that first we can have in a system level and next in a component level. Now, today I'm talking only about the system level. Now, the analysis can be done in different levels of sophistication. The basic, which we wish even the undergraduate students to be aware of, is the equivalent static analysis, neglecting the time-wise variation of wind. However, for some very special structures like tall masts, okay, or suspension bridges, you have to go for dynamic analysis. And if you want to understand that what is the interference effects of different buildings, whenever there's a cluster of buildings, say in the downtown area of a city, then you have to go based on the experimental method, which is based on wind tunnel tests. Now, today we are covering only the equivalent static analysis as per IS 875. Now, what are the steps? Let's just have an overall idea that since the wind load depends on where the building is located, first we need to get a basic meteorological data, which for the engineering purpose, it is the basic wind speed at a certain location. It can come from any direction. We are not worried about the direction. Now, this basic wind speed is given at a certain height based on anemometer readings. Now, from that basic wind speed, we are having some modifying factors by which we calculate the velocity at the different heights of a building. If the building is very small, it's a low rise, then whatever is the basic wind speed, which is for at a height of 10 meters, that is considered to be constant throughout. But if a building height is more than 10 meters, then you will consider the variation of the velocity with a modifying factor. Now, from the velocity, then you calculate the pressure on the surface which is obstructing the wind flow and normal to the direction of the wind flow. That means you have to consider a projected surface of obstruction. And that is calculated based on Bernoulli's theory, but in the code it is given in a simplified expression for the Indian conditions. See, some of these expressions you will find difference in the other codes. Now, once I know the pressure, then I calculate the force, which is the pressure times the area perpendicular to the direction of the wind flow and normal to it. Okay. Now, whenever we are talking of a tall building, definitely we'll be computing story by story, or I would say level by level. That means at a certain level, you have a tributary area of obstruction from the mid height of the story below to the mid height of the story above. For that level, what is the force? Then you go to the upper story. Like that, you have to compute. Now, the basic wind speed is given in a wind zone map. Now, this itself has some probabilistic information built in it. It is based on peak gust velocity of wind for a return period of 50 years, which is the typical building lifespan, at a height of 10 meters from the ground level. What is meant by gust? That the velocity has local peaks. Then which one would you consider? Will you consider the highest peak? It says no, we don't have to. We can average the value within a wind interval of 3 seconds. and that value is called the peak gust velocity. That means there will be a distribution of this velocity throughout the day, throughout the month, throughout the year, and over several decades. Now, once you go through this data, then there are models based on which these wind maps are generated. Now, in India, the wind map appears like this. I would, whoever is from India, I would say that please know the value of this basic wind speed of your hometown. The lowest one is, say, 33, which is in the rain shadow area of Karnataka. That means that is the area which is girded by the Western Ghats. 33 meter per second is the basic wind speed. Next is the yellow region, which is most of our Deccan Plateau area, which is 39. Next is the 44, where we have the Andhra Pradesh and certain parts of Orissa coming in. Now, Chennai is a coastal area, and this comes under this 50 meter per second basic wind speed. And there can be some regions in Leh and in states like Mizoram, Tripura, where the wind speed can be even higher, and the basic wind speed is considered as 55 meter per second. Now, once I have this VB, then we are having some modifiers. Now, these modifiers are trying to make the complicated story simple. What is K1? K1 is a risk coefficient, because if you are designing an important building, you will be having a value of K more than 1. Now, how do you mean important? It's a target design life. That means this is the basic wind speed is for 50 years. If you are targeting a building for 100 years, okay, then obviously you have to go for a higher coefficient. K2 is a terrain and height multiplier. Now, depending upon the terrain with the height of a building, these values are given in the code. K3 is a topographic factor. That means, say in a valley region, see in the a few months back, the Beta Valley was in the news. I myself visited that place. That means there in the valley region and in the top of the hill, the values of K will be different. And the fourth is the importance factor in cyclonic regions. That means if I look into this whole east coast, there can be buildings like cyclonic shelters, the emergency buildings, for which you have to consider another extra factor. But for the conventional buildings, we don't have to consider that. That means there are 4 factors, K1 to K4, which you multiply to VB to get. Now, please note, K2 is a factor which depends upon the height, and hence Vz is now dependent on the height. Now, from the Vz, then you calculate the pressure by this relationship. This is unit dependent. Please note, Vz has to be in meter per second, and the pressure that you get is in Newton per meter square. This coefficient is an average value based on the Indian conditions. If I have to design for cyclones, then this Pz is modified based on what is called a directionality of the wind. But again, most of the time we will not be designing from which direction the wind is flowing. We will not be doing that. Next comes the system level analysis. That means once I'm able to find out this pressure, then I'm trying to calculate the force at a certain level based on a coefficient. So what is this coefficient? This coefficient is the dynamic characteristics of the building, which we get from a certain chart. I will show the chart in the next slide. What is AE? It is the effective frontal area of obstruction. That means if the area of obstruction is curved, you take the projected area, okay, for that particular level, whatever is the tributary height, the width, like that you calculate the area and multiply by the pressure, you get the force at that level for that particular area. Now, this is a chart which gives the value of CF. I have just picked up only one chart from the code, which is for the simplest case. a rectangular block type of building. And as Professor Liberato was saying, that there are what is called the suction effects, okay, the turbulence effects. And based on this CF coefficient is determined. What are the parameters? One is h by b. H is the height, b is the dimension of obstruction, okay, the horizontal dimension. And the other parameter is a by b, where a is the direction along the wind flow that you are considering, and b is the direction perpendicular to the wind flow. And these sketches show that how you have to pick up the dimensions based on the directions that you are considering. Now, if I go into the component level, then the story gets a bit more involved, because for the overall system level, whatever coefficient is given, that's enough. But for a component level, it depends upon the inclination of the component. Whether it is like a gabled roof, whether it is something else, it depends on that. And there are several charts in the code 875 which gives the coefficients for the component level analysis. I would say for wind, the component level analysis is more difficult than the overall analysis. Okay. In the component level analysis, we have two coefficients. The first coefficient is called the external pressure coefficient, and the second one is an internal pressure coefficient. Now, please note, external pressure coefficient is considered to be positive, and the internal pressure coefficient, which is usually a suction, is considered to be negative. Now, negative of negative means it becomes an additive effect. That means the external effect and the internal effect, that adding to the dislodging of the component of the building. Okay. A is the area of the component, which can be a facade wall, or it can be a roof, and PZ is the level of that component. Now, let's try to understand the steps that as a student, where do I start? That first, what I can do is, a building, I am viewing it as a two-dimensional, a regular configuration building, two-dimensional, as if there are n levels, but the first level is the first floor. Okay. And height of these levels, please note, are from the finished ground level, Z1, Z2, like that. Now, this system can be thought of as a stick model, because we are doing an overall analysis, and as if I am lumping the masses at the different levels, and I have to calculate F1, F2, like that up to Fn. And how do I do that? For each level, I will consider what is the tributary height. That means for level 1, it will be from the mid height of the ground story to the mid height of the first story. That is my tributary height. What is the area of obstruction? That is the total, that means height times the length of obstruction is the area, and then we multiply by the pressure to get this force. Okay. Now, the summation of these forces, F1 to Fn, that is called the base shear. The idea of the base shear means as if the wind is trying to shear off the building at the base. That is, what is the base shear? Base shear is a summation of the forces. And another important thing we also have to note, at least in the stick model, is the overturning moment. So, what is the overturning moment? It is, please note, the overturning moment is for the foundation. And for the foundation, it is not, the height is not from the finished ground level, but it should be considered from the top of the foundation. That means the overturning moment, the resultant overturning moment is F1 times H1 plus F2 times H2, like that up to Fn. That is the total overturning moment. And see, you should learn how to do calculations fast. Once you have an estimate of this, then you can go for a computational model. What you do is, typically you will be doing the calculations in a chart like this. This is the way my teacher taught me, and this is the way I teach my students. That you, on the rows at the different levels, you write the height of that levels. This is from the ground level, because please note, K2 is determined from the height from the ground level. Whereas when we calculate the overturning moment, it is from the height of the level from the top of the foundation. Determine K2 from the table, determine the velocity, pressure, area, and force. This is the summation of the forces, force times the height. The summation of the forces is the base shear, and the summation of this force times the height is the overturning moment. That means in a neat, compact table, you can calculate these results. Okay. Now, typically, the analysis is performed at two orthogonal directions. See, whenever we analyze a building, we typically prefer an orthogonal direction. Why orthogonal? Because if you analyze one direction at a time, then you can cater for if the wind comes in some other inclined direction. That you do it for the x direction, do it for the y direction. If the building is regular, you do not have to do any more addition. If the building is irregular, then again some other involvement is necessary. Next comes the design, very briefly, for I would say only low-rise buildings. See, whenever we do a design for wind and earthquake, it's not just the nitty-gritty calculations we have to be starting with. We have to think of the building as a whole in a system level. How to reduce the effect, that's the first thing. Okay, let's be defensive rather than offensive. Okay, we should use what least area of obstruction. That means there was one photograph shown by Professor Liberato in Milan where they went for an aerodynamic shape. All these buildings like Burj Khalifa, they are aerodynamic shape. That means from that conceptual stage itself, they are giving importance to the wind obstruction. Okay. Now, if I'm not going into other devices for tall buildings, that's a topic by itself. I'm just talking of for low-rise buildings. For reinforced concrete building, whether it is cast in place or whether it is emulative precast, just an overall analysis is enough. But if you are having facade elements or if you are having some lightweight roof, then you have to do definitely a component level analysis. And in the design, you have to provide adequate hold down devices, and you have to provide horizontal braces at the roof level. When we visited the factory yesterday, or not Saturday, I told you to look up to see what type of bracing they have used. Okay, at 5 bays, they have used bracing at the horizontal level for the roof. What for was it? What for it? It is for to have substantial stiffness against these lateral forces. Otherwise, the roof, those rafters will try to slide against each other. Okay. For mid to high-rise buildings, there should be adequate resistance for the lateral loads in terms of stiffness and strength. Typically, for reinforced concrete building, it's not an issue. If you're talking of wood buildings or low-cost houses, then it can be an issue. But otherwise, for reinforced concrete building, if you're designing for gravity loads, if you're designing for the overall component system level analysis, then you can get the resistance. Okay. Next comes the analysis for earthquake forces. Now, earthquake force is a misnomer. It doesn't apply any force as such. It is a ground motion. And the masses at different levels, they are not able to keep up with the ground motion because of the inertial effect. And since they move asynchronously with the ground, it generates forces in the supporting members. And those forces, we tend to call it earthquake forces. That means it's an inertial effect which generates the forces within the members. Okay. Heavier the masses, more are the inertial forces. Please note, this is another concept. In wind, we said lighter the roof, we have a problem. Lighter the facade, we have a problem. But here we are saying heavier the masses, we have a problem. Okay. What are the features? Again, earthquake primarily acts in the horizontal direction, but several earthquakes have shown that there can be vertical components. Even the latest major earthquake, the Sagaing earthquake in Myanmar, had substantial vertical component. You can talk with our Professor Raghukant, he will be able to describe about that. He works in engineering seismology. Earthquake is also dynamic in nature. Okay. It is reversible. This also depends on the location of the earth. That's a whole topic by itself, the earth geotectonics. It depends on the type and deformation of the soil. That means once you are trying to do some seismic hazard analysis, you are trying to get the base rock motion. But then depending upon the soil fill, the earthquake motion can change. Okay. Earthquake causes nonlinear deformation of the members. Now, this is quite different from wind. In wind, we try to design for elastic resistance, and elastic analysis is considered to be adequate. Whereas earthquake, from the very beginning, we say that we cannot afford to have elastic behavior unless it's a very high-end structure like nuclear reactors. We have to accept damage, but it will be a controlled damage. Okay, that's what we was talked about in our detailing. And however, we are not doing a nonlinear analysis per se in our day-to-day analysis. We are doing again an equivalent linear analysis, taking care of this nonlinear behavior by certain factors. And earthquake is uncertain. Another difference is wind can still be predicted. Earthquake cannot be predicted. That's a major challenge still ahead of the human society. The analysis can be done in different levels of sophistication. The equivalent static method is what we are going to cover today. Here we are converting the inertial effect into like static forces, okay, only in the horizontal direction. Next, you can do a dynamic analysis where it's a set of differential equations which you are solving by some numerical techniques. There are two types. One is the time history analysis. The other is the response spectrum method, where you consider the dynamic properties of the system. What are the dynamic properties? First, you have to calculate the time periods, and for each time period, what is the mode shape. There can be a nonlinear static analysis where you are considering the nonlinear behavior of the material under a certain level of earthquake, which is called the pushover analysis. And then can be a nonlinear dynamic analysis, which is equivalent to time history analysis, but now you are considering the nonlinear behavior of the materials. Besides this, there can be an experimental method to estimate very unique type of structures which we cannot just do get a confidence based on computation. Now, today you will be seeing this in our lab. We have a small scale shake table, but good enough for our research purpose. Okay, where here you can see a specimen for storage racks. And here you can see that the masses have been provided to simulate certain inertial effect. And here the base will be moved and not the force will be applied. Just adjacent to it, you will be seeing the reaction wall, which is used for what is called quasi-static tests. There we are not shaking the base, there we are applying the force horizontally. Now, how do I do my analysis for the forces? Analysis means computation of these forces for the equivalent static method. We are trying to compute the total force over the height, which is called the base shear. Now, this base shear is a function of the weight of the building. What is the weight? It is a summation of the weights of each level. Okay. To that, you multiply a coefficient. Now, in this coefficient, you are trying to bring in the parameters which at least can be brought into numerical terms. Z is the factor which corresponds to a certain zone. This is divided by 2 to make the design more economical. Okay. I is an importance factor which is applied for buildings like hostels where we have so many number of persons at a time. R is a reduction factor because finally we are doing an elastic analysis, but we will be doing an analysis for lower forces, and that reduction is based on the ductility that we expect in the building. What is ductility? It is the ability of the building to deform laterally without giving up to a certain extent. Okay. And this weight, as I said, it can be computed based on the weights of the each level. Now, this is the description. I will just skip. Now, quickly to show the seismic zones. So, our country is divided into right now 4 seismic zones. Please note this code is under revision and we will see another higher zone coming up. Okay. Now, right now I am just sticking to what is there existing. Zone 2 is most of the Deccan Plateau area, the Rajasthan area, and there I will go to the values once again later. Then comes zone 3, which is the Vijayawada area. Chennai comes under zone 3. Zone 4 is the Gangetic belt, Delhi, Kolkata, even Mumbai is zone 4. And then we have zone 5, where parts of Gujarat, parts of the Himalayas, and the full northeast comes under zone 5. Now, this is the table which gives an idea about the ground acceleration with respect to the acceleration due to gravity. Okay, that's the way you can view these values of zone. That for zone 2, it is 0.1, it is 1/10 of the acceleration due to gravity, whereas for the zone 5, it is about 36% of the acceleration due to gravity. This slide talks about some idea about the importance building. I would skip for the sake of the time. For most of the building, we can consider I equal to 1. And the value of R, as I said, that we inherently assume that the behavior will be ductile. Now, if I want to pay for the ductility and try to reduce the force, that option is given to us. I can have a higher value of R, but I have to pay for the more intricate detailing. Whereas if for most of the buildings, I may not go for that type of detailing, and I can take R is equal to 3 for the reinforced concrete buildings. Now, the SA by G, let me just go back once again. This particular value, I would say this is the most important value which quantifies the dynamic effect of the building. Now, from your high school knowledge, you can think that this is equivalent to the resonance of a vibrating system. Given that the earthquake is highly erratic in nature, this type of design spectrums, which are smoothened curves, have been suggested, which is a function of the time period. Please note, in physics, we talk about a function of the frequency. Even for machine vibrations, we talk about functions of frequency because it is convenient to handle them. Whereas for buildings, since the for us the time period is more convenient to handle, and hence the response spectrum. These curves are called the response spectrum. Why spectrum? Because it is a curve with respect to the different frequencies. Frequencies or time periods. And the maximum value is capped at 2.5. There are also reasons why this capping is done. Values can, in actual earthquake, it can be more than that, but for design purpose, it has been capped at 2.5 by considering that there will be inherent inelasticity. And there are 3 curves given for the different types of soil which can be there over the rock. If you are building something on the rock itself, then this is the bold line. If you are building something on soil, then the values increase for a certain time period. Now, once you know the base shear, then you have to distribute that over the height of the building. And that distribution is done considering the first mode of vibration, which is parabolic in nature for a regular building. And this is the way the forces are calculated, where h is the height of a level from the top of the foundation. And here also I can have the stick model. That means given the levels of the building, I will consider as if at the different levels the masses are lumped. I need to compute Q1, Q2, Qn. That means first I will be computing the base shear, and then I will be distributing that base shear over the height. Now once I know these forces, I can also compute the overturning moment, and I can do the full structural analysis of the building. But first I would say strongly suggest that you have an idea about the stick model. Okay. And this is a type of table one can use that for the different levels, compute the weights, compute the heights from the foundation, and then you can compute the different forces. The summation of the forces is the base shear, and summation of the overturning moment is the total overturning moment. Now coming to the design, what do we wish? We wish lightness of the floor masses. In our country, what has happened is there is unscrupulous, sometimes extension of a building, adding of 2 stories. It is dangerous. And then the corporation comes and tries to knock them off. People are building swimming pools in the top of the roof. Okay. Integrity of the members for continuous load path. Now, this is very important for the precast buildings. That how do I ensure that the members are connected? And we had talked about the emulative connection, which is the most common in our country. And what we saw in BJ's case, that they are doing emulative connection, which is suitable for both durability as well as ductility. Avoidance of large cantilever projections, regular in configuration. What is meant by the word configuration? How your building members are laid out. Adequacy of the foundations, very important. The taller the building gets or the softer the soil, there can be problem. Ductility in the members, it depends upon not only the reinforcement but also on the connections. And if the building has certain projections in plan, we can isolate them. Okay. The staircase has to be properly designed so that it doesn't fail during an earthquake. The 4 basic mantra: robust configuration. Robust configuration, that we should not invite trouble from the beginning itself. That's where comes the conceptual design. We are not restricting architectural innovation, but we are trying to have the basic skeleton of the building in a robust way. We should have a minimum lateral stiffness so that for small shaking which happens, say in Guwahati, things should not fall down. You're going for lunch and suddenly something happens and falls on your head. That's it. Okay, it shouldn't happen like that for small earthquakes. For large earthquakes, there should be strength, that the building should not come down. And the last one is the adequate ductility. This is where most of the research goes, that how I can make, which is concrete, which is inherently brittle, how can I make it ductile? Okay. With reinforcement, both steel, these days also we are having fiber reinforced concrete. Now coming to the configuration, I'm just very briefly mentioning this, that the configuration is studied in terms of what is called irregularities in plan or in elevation. What is meant by irregularities? That these are the features we wish to avoid. If we are not able to avoid, then we have to take care of it. It's a torsional irregularity. Today, Professor Liberato was talking about the torsional effect. If there is the floor diaphragm has certain corners, there will be stress concentration. If there are large openings in the diaphragms, there will be problem. Out of plane offsets of the frames, if the frames are not properly placed, or non-parallel alignment. Similarly, in elevation, a big problem in our country is our cities don't have proper parking space, and we are utilizing our ground story for parking. And that creates what is called a soft story effect. Unless we continue the core walls, it can become soft story. That means its stiffness is much less, compared to the stories above, and it also tends to become a weak story. That means its lateral strength is less than the stories above. Vertical geometric irregularity happens in a podium and tower type of buildings, where suddenly a tower comes up from the podium. Whoever has visited the Phoenix Mall, you can have a look into it. In plane discontinuity of the members, if the members are not in a plane, then typically sometimes these beams are offset because of functionality requirement. But we have to see again what Professor Liberato said today. I will repeat that we should have at least 2 frames in the 2 orthogonal directions, which are well defined frames. Okay. Floating columns or small columns can create trouble. Irregular modes of vibration also should be avoided. Now, coming to the structural analysis, now once I know these forces, then how do I do the analysis? First, I have to start with a model. What today you will be doing is a stick model, one-dimensional model. But I need to know the forces. Next, you can go for a 2-dimensional typical frame, where in your undergraduate you have studied the portal method or the cantilever method, and you can do it by hand for a simple configuration. For a more exotic type, you have to go for a 3-dimensional model. Now, for each direction, you have to calculate the design forces at the different levels, whether it is wind or earthquake. You have to do the same thing. This is independent of wind or earthquake, same procedure. Analyze the building, and then you have to combine the internal forces due to the wind or earthquake along with the gravity. And these are the load combinations specified in our code. This can change from code to code, and hence, if you are working for some other code, please be aware of this load combinations. Okay. Since either wind or earthquake can act in any horizontal direction, the corresponding value itself is a combination of the values of the external loads acting on the selected 2 orthogonal directions. What I mean to say is that whatever earthquake load has been considered in the combination, there you have to consider the effect of earthquakes in 2 directions, not simultaneously, but it is called 130% rule. There is another rule called the summation of the square root of the sum of the squares. Like that, you try to take account of earthquake coming in any direction, but now you are trying to decompose it along the x and y direction of the building, and then try to see what is the final effect by after combination. For service checks, what do we do for service checks? Primarily, it's the drift. For vertical load, we check the deflection, whereas for the lateral load, we check the drift. Too much of a drift will lead to what is called a P delta effect. Some stability issues will come, especially if it is a tall story. Also, it will lead to the damage of the non-structural components. Now, in the last 5 minutes, I will go through this computer-aided analysis. Now, I would strongly suggest that as an undergraduate, try to pick up at least one structural analysis software. Get familiar so that when you go to a design office, you do not look, a total novice. Student life is the best time to learn. One of our directors said that let the students make mistakes, encourage them to make mistakes. Why? Because once they graduate, they cannot afford to make mistakes. What a profound statement. Okay. Now, coming to the computational model, it's a matter of getting used to the software. Okay, I am stating something independent of the software, generic. First, the type of structure that you are selecting, it defines the way you develop the model. A bridge is modeled in a different way compared to a buildings, compared to a transmission line tower. We have to select the member sizes, which are typically based on certain rules. That deflection based span to depth ratio governs the depth of the beams. Selection of the material properties, which is typically from the contractual document, and then you develop a computational model with a software, analyze and you consolidate and interpret the results. The models can be developed in the software using standard templates, but I would suggest that as a beginner, you should not use the templates. You have a chance to make mistakes. But when you're knowing what is the software doing, you can use the templates very fast. Otherwise, you define the nodes. So the way a survey is done for a building, first you fix the nodes where this, say, this particular shed is coming up. How will you place the shed? You need to know the locations. Similarly, you have to define the nodes, then you have to connect the nodes with the members, assign their section properties, material properties, the loads, and the load combinations. We have to select appropriate finite element to model the components, the frame elements for the beams and columns. Joints are considered to be rigid for an emulative connection. Shear walls can be modeled using equivalent, and if there is a brace, then some axial elements. Infill walls also should be considered as strut elements. The code has given certain guidelines, and the boundary conditions. Now, this is very important. When I was talking about that chapter in the handbook about the seismic analysis, or I would say the structure analysis, the main issue with the precast buildings is what is the boundary conditions of members you should select. That means you should know what type of detailing is being done. Luckily, in our country, it's all mostly emulative, whatever you have seen in BGCK. And emulative connections is same as like a monolithic connection. Okay, I will skip this. Now, this is something, if you don't have a design data for an existing building, then you have to do some condition assessment. Modeling of the loads, self-weight, typically the softwares consider them, I mean, it is implicit, but superimposed dead loads, whether it is a floor finish, whether it's a roof finish, you should compute that. Dead loads of heavy supported elements like slabs, typically you may not have to model the slabs, you just compute the load and transfer it to the supporting beams. The live load and the lateral loads. This is where comes your analysis for the wind and earthquake, to know what are the forces for which you're going to analyze. And there can be some special loads and the load combinations. Now, whenever you have done an analysis, you should do a self-check. I am teaching this you that as whenever you're doing the calculations, you have to do a self-check. Similarly, your model, it's your responsibility to make sure it is correct under the assumptions. What is the minimum check? That the weight of the building should be equal to the sum of the reactions. That means you compute the weight quickly and see whether the reactions is coming as per the analysis to a reasonable tolerance. The lateral forces should end up to the base shear that you get from the analysis. Study the bending moment, shear force, axial force diagrams. My tutorial 2 was based on these diagrams. That as a designer, unless you have a inherent feel or intuitive feel of the analysis, you are not a good designer. Okay. Then you have to get the envelope diagrams. Envelope diagrams comes after the load combinations, that what are the maximum value at a certain section after all the load combinations. Then you pick up the demand values at the critical sections. Say for a beam, we will be designing for the span or for the support region. Then we do the deflection checks and the drift checks. Conventional design objective is that we have to make sure that the internal force demand is less than the capacity that comes out from, say, RC mechanics. Okay, or the other way around, that the capacity demand should be greater than 1. And in the serviceability, we have to make sure deflection is limited and the drift is limited. Now, this is my MTech student had done more than 20 years back. Just to give an idea, I show the same problem. This is a residential building with 4 apartments in one level. We are going to see the results of one particular frame. This is the computational model where we are considering pinned foundation based on the isolated footings. If it's a raft foundation, you will be considering fixed. Okay. This is the elevation without any irregularity. Gravity load analysis, you are assigning the slab loads. How do you transfer the slab loads? We study in our undergraduate that whenever a slab is supported on all the 4 sides, we use a triangular and trapezoidal rule to transfer the load to the supporting beams. In this model, the slabs are not modeled. The loads are transferred to the supporting beams. Similarly, in our Indian context, there can be heavy brick walls. The brick walls should be the load should be modeled. And these are the bending moment diagrams. Try to have a feel that whether this diagram makes sense or not under the gravity load. Okay. Similarly, the shear force diagram and the axial force diagram. As you go down the building, the axial force is getting cumulative. Coming to the lateral load analysis for the earthquake, first we have to define what is called the center of mass. Now today, Professor Libarupa had mentioned this, that see, even in our basic physics, we had learned the term center of mass, or sometimes for floating bodies, center of pressure. Why do we define this? These are analysis variable. That whenever you have a distributed force, it's modeled to model this distributed force. Difficult. Hence, we apply the resultant on this center of mass. Now, if the diaphragm is disturbed because of cutouts, then you have to have two different centers of masses. And then comes the torsional effects, which by design centers of mass, I'm skipping those. We have to assign diaphragms. Diaphragms means as if all the nodes at a certain level will try to move together. And this is the way you compute. Now, whenever you are in a design office, you should keep this recorded, so that if someone is doing a proof checking, or say 30 years down the road, someone is checking whether the building is adequate to have another extra story, then they have to see the calculations. And that's why neat calculations are required. Okay. And this is the way the force looks in a stick model. And today you're going to do this. Then you assign these forces in this three-dimensional model at the different levels. I will skip. And these are the bending moment diagrams under the lateral forces for that particular frame. Please note, these bending moment diagrams are quite different from those which we have seen under gravity loads. Sometimes engineers think that, okay, anyway, there is safety factor in gravity load design which will take care of lateral loads. That's an utter foolishness, because the critical sections are quite different. Values can be quite different. Okay. These are the shear force diagrams. That means as you go down the frame, your shear force increases. And finally, the bottom, the reaction of all the columns should be equal to the base shear. And this is the axial force diagram under lateral loads. There is a little bit of cantilever effect, one side tension, one side compression. Closure. Let me read it out. This is an important, because a full 1 semester course I finished in 1 hour, right? It can be observed that the member force diagrams under lateral loads are quite different from the corresponding diagrams under gravity loads. That we have to appreciate, that these are two different ball games. After the values of an internal action at a section of a member are combined based on the load combinations, the maximum numeric value from the envelope is selected for design. From here onwards, you now go whether you are, if it's a structural steel, you have to pick up the steel members. If it is a reinforced concrete, you have to pick up the reinforcing steel. A design value including the effect of lateral loads can be substantially high and reverse in nature as compared to that under gravity loads alone. For example, a section of a beam near the column support may have to be designed for both sagging and hogging moments. Okay, with this, I am ending the story.